Okay, so you can see the screen now. Basically, this presentation, we're going to talk about LED, 24-hour lighting in greenhouse weighted production. Let's go directly into it. So why we need to go to 24-hour lighting? So we are now using 16-hour lighting, right? So, so why we want to go to 24-hour lighting? One of the things when we talk about the lighting, there is 4 aspects we need to think about. The intensity, photo period, spectrum, and their distribution, like inside the crop canopy. The total amount of the light received by the crop during 1 day, that's called a daily light integral, is determined by the intensity and the photo period we give to the crop. The DLR, or daily light integral, have a major influence on the plant growth and yield, just like the Dutch, talking, 1% light, 1% yield increase. When they talk about that, is talk about the DLR. So there are a couple of ways you can increase, the DLR to achieve your target DLR. One is use, of course, low intensity and long photo period. Another one is use, shorter photo period but high light intensity. Use a long photo period, that's up to 24-hour a day, and the low intensity, of course, have a certain advantage. First, you have a low light intensity, means you have a less light fixture. That means you have a less fixture cost. The other thing is less light intensity, low light intensity. That means you're going to be use less electricity in any time of the day, especially during the daytime. So you also, move some of the light to the night. So during the off-peak hour. So during the off-peak hour, the electricity rate is low, so you can save some money. Many greenhouse growers, especially vegetable growers, have adapted supplemental lighting for year-round production. Based on a study sponsored by the IESO, the Independent Electricity System Operator, that's the power grid manager for Ontario, we're going to have like over 1,000 acres of greenhouse using supplemental lighting, especially in Kingsville and the Leamington area. So they are doing some major investment, to bring power to the area. But even they're doing that, there is still not going to be having enough power during the peak hour, let's see, from 5 a.m. to 11 a.m. during the winter time. So they basically ask us to develop a demand side solution to cut down the peak power demand at least by 18%. One of the easy solutions for do that, of course, is using or adapt energy efficient LED light. The latest LED, they have a photon efficacy around 3 compared to the most energy efficient HPS now, the double-ended 1,000 watt HPS, that's around 1.7. You can cut down the electricity use by 40%. So that's actually more than enough. But the problem with that is the LED is very expensive. So for greenhouse fruiting vegetable, we talk about $1 million an acre. So if you include everything, the wiring or the power supply, all that thing together, so the LED is still going to cost 3 to 5 times more of the HPS cost. So that's a major barrier. So if we can use 24-hour lighting instead of conventional 16-hour lighting, we can cut down this cost by 1/3, okay? Then we also cut down the 1/3 in the daytime light intensity or the daytime electricity use, reduce the peak power demand by 1/3. So that's the thing I mentioned, the first 3 benefits. So for Google 24-hour lighting, we could also improve the overall energy efficiency and also prevent light pollution by facilitate the use of a light abatement curtain. Here is the energy demand in a double poly greenhouse. That's an extra commercial greenhouse for tomato production with or without light abatement curtain. And the heat released by the light fixture at 210 micromole for 16 hours. That's basically the current lighting control strategy. So this on a day in the February 26th, so is overcast day is quite a representative date. The brown line, this is the actual heating demand. Okay, then the green line, this one is the heating demand with the use of a light abatement curtain. Because once we put on light abatement curtain during the night, the heat loss to the other side will be reduced by 50 to 75%. So you can see the heating demand is significantly reduced. So when we put the lighting, all the electricity you go to the light fixture, only about 2 to 3% actually converted to the food by the plant. The rest of them will be eventually converted into heat. So you see this dotted line, basically we use the HPS light. So that's we have 1 a.m. on, 5 p.m. off, basically for 16 hours. That's the heat released by the light fixture, contributed by the light fixture. So you see, it's well above the heating demand, whether we have a light abatement curtain or not. So that means this heat, we need to winter them out, blow them out. Otherwise, we're going to have a high temperature stress to the crop. For LED, this one is the efficient LED. You see, with a light abatement curtain, we are okay, right? So we not have only have a little bit excessive heat. But when we use a light abatement curtain, we're going to have you see this line is well above here. So we still have a lot of excessive heat and high temperature stress. We still need to blow the heat out. So on one hand, we blow the heat out. On the other hand, the after 8-hour darkness, we still need to burn natural gas from the boiler to supply the heat. So on one hand, we blow out the heat. On the other hand, we burn gas to supply heat to the greenhouse. So that's really not an effective way to manage the energy. Now, let's move into the 24-hour lighting. What's going to happen? So now our light intensity will not be 210, will be 140 micromole for 24 hours. You see, this is the heat released by the HPS light. So with the light abatement curtain, yeah, you see, roughly the same. The heat released by the light fixture will meet the heating requirement. We don't need any additional heat from the boiler anymore. So, but we still have overheating in the night if we use a light abatement curtain. So if we use HPS, we cannot use a light abatement curtain. We cannot. If we open the curtain, of course, you're going to have a light escape, you have a pollution. But if we move into LED, you see the heat release is equal to the heating requirement. So we don't need any heating and we don't have any overheating. So similar like with the LED, the light abatement curtain, we're going to have a very good energy management. Overall, high energy efficiency also prevented the light pollution. So it's really environment sustainable. So people are not going to complain. So all this sound really good. So the next question is this feasible? So actually we have one very big challenge to make this thing work. That is the plant, just like a human, they need a sleep. They have a biological clock. If I have the full period is more than 17 hours, we're going to have leaf chlorosis, then we can have a reduced yield increase or no further yield increase. There are a lot of hypotheses for that. The reason, we have a 24-hour lighting, too much starch built up in the cell, damage the membrane, the biological clock, and the high temperature stress from the HPS light, or integrate temperature and the light signal pathway. So my personal opinion and or belief is, I think, probably is caused by an integrated temperature light signal pathway. So the hypothesis is more on that. So later I'm going to talk about how I use that hypothesis along that path, try to find a solution for this problem. Before go further, I want to mention something about the chlorophyll fluorescence. So it is a good indicator for stress, and it's much more sensitive than our eye. So normally the number 0.8 is really good. So below 0.7, we still start to see some damage or stress. You see this one, the bottom one, basically, yeah, we have some stress, you see. So we start find a solution, first look into the temperature. You probably aware, a lot of people probably aware, when they want to go to sleep, you lower your room temperature. So we will see, okay, we can do the same thing on the plants. So we have a pre-night temperature drop. So then we quickly resolve the temperature. What we did when we're doing that is when we lower the temperature, so you see the leaf temperature drop quickly, this green line. So, but the fruit temperature, because they have a low surface area, so they drop slow. So we heat them back. So because the fruit, you see close to the heating pipe, so they warm up quickly. So by doing this, we actually generate a difference between the leaf temperature and the fruit temperature, so a warmer fruit. So the fruit, because it's warmer, they grow fast. Actually, in this way, they can utilize the additional sugar and the starch, made and the long food period lighting. So then we test this hypothesis, over basically 4 winter, 2 winter on tomato, 1 winter on sweet pepper, 1 winter on cucumber, use 8 greenhouse. In this trial, we basically use top high pressure sodium lighting. For the interlighting, we use the LED light. So we ran the trial. So this is basically the temperature setup. You see, after we shut off the light, right away, you get a quick drop of the temperature. For the tomato, you drop down to 13.5. For pepper, you can drop down to 15.5. For cucumber, you can drop to 12.5. So that's the low temperature threshold. That's need to be really careful. When you drop the temperature, don't want to drop below this level. Otherwise, it can cause crop damage. So with this strategy, we were able to significantly reduce the leaf corrosis on tomato and sweet pepper, but not much on cucumber. We also able to increase the yield by 10 to 30% at the long flow period, at the 19 hour or 20 hour. That's depending on the cultivar. So we also able to save some heating energy during the cold winter months. One thing I wanted to mention, with this temperature control strategy, we are able to reduce leaf corrosis, but still cannot completely eliminate the corrosis. You see this one, at the regular temperature control, you have a lot of corrosis. With the temperature drop, we have much, much less, but we still have corrosis. Okay. The other thing is we can still do only 19 or 21 hour. We still cannot do 24 hour yet. So the next step then I try to look into is the light signal part. One of the things with the continuous light beside the corrosis is when under the continuous light, the leaf become smaller. The plant become more compact, so they reduce the light interception. So let's see how can find a way to increase the plant height or the leaf area to intercept more light to improve the growth. One of the things I'm looking into is this phenomena is with 100% of blue light or monochromatic blue light. When we use blue light together with the other light, so you increase the percentage of blue light, what it does, make the plant more compact and a smaller leaf area. But once you reach 100% blue light, so the effect reverse, the plant are taller, the leaf are bigger. So I say, okay, how can you use 100% blue light? Yeah, the only thing is we can achieve 100% blue light is during the night, right? So in the daytime, we always have a sunlight. You can never achieve 100% blue light. So then we test this new concept. So in our control, basically red and blue together, 200 micron red, 50 micron blue. Then we have a 12-hour darkness. Then in our new continuous light or the 24-hour lighting, basically we put a 200 micromole during the day, then a 50 micromole during the night. So that's how it looks like. You know, the control, you have red, blue together, this is the purple. So then you have red during the day, blue during the night, and to a surprise, the plant grew at the continuous light, doing really well. This is how it looks like. So the CL is continuous or 24-hour light. You see the leaf is more flat. All we are seeing you see is more flat. They have no leaf chlorosis. The plant are taller with a large leaf area. It can intercept, you know, more light. So the one with the red and blue together, you see some of the normally the leaf symptom we show go with normal lighting. The leaf, you know, they are not flat. So it actually intercept less of light. They more kind of like avoid the light. So because of that, we end up a significantly high yield. So in the first 4 months of harvest, we get 15% yield increase. So in the rest of the months, we did not see much of a difference. So basically, this strategy completely eliminated the leaf chlorosis. We also look into, you know, the leaf chlorophyll fluorescence image. I mentioned it is more sensitive to detect the damage. Even with that, you see the CR content, we don't have any damage. So a lot of work in this trial was done by Jason at the time, who was a PhD student at University of Guelph. Of course, now he's a scientist at our research center. So he worked really hard. You see, he measured both the photosynthesis, actual photosynthesis during the daytime and during the night. So the daytime, not much of a difference. Not significant. In the night, you see the one when we have a darkness, the respiration consumed a lot, but the continuous light, we don't consume much because the photosynthesis made enough to compensate for the photosynthesis, for the respiration. So actually over the 24-hour, the continuous light made more sugar and starch. That's why we get a high early yield. So now the concept have been proved. So we expanded the research in the last winter. So because that time we proved the concept, we just use 12-hour, you know, the same length at the daytime. So normally, of course, in the greenhouse now we use 16-hour. So we use that one as a control now. So also we try to reduce the daytime intensity or reduce light fixture cost. Then we try the 16-hour red and the 20-hour red. Of course, we also try the negative control. People say, hey, you try the red blue for 20 hours. That's 1/3 of the 2/3 of light intensity. Some people also ask, oh, why you reverse, you know, the red blue, the daytime reverse to see what happened. So then we also did the red blue together, you know, then have the red or blue during the night. With this one, we can do like a 106 micromole during the night. So you see here, we see you know, clearly damaged. When we have the red light is longer than 16 hours. When we have 20 hours, you know, the 24 hours or the reverse and day night, we have a lot of damage after basically 2 months of continuous light. So after 3 months, when we get into March, surprisingly, you see the damage is much, much less. So the sun light, we have helped the plant to recover, to repair the damage, but we still have a damage on the, you know, the 24-hour lighting, the red and blue together. Now we look at the photosynthesis. You see the 16-hour, we don't have a reduction, you know, during the daytime, but the 20-hour, we have a reduction. But in the later production period, you know, we no longer have a significant reduction for the 20-hour. Basically, also the sunlight helps the plant to recover. So now we look in the night. You see the night, the 24-hour, you know, this red, blue together, 140 micromole, this 200 micromole, a lot of light. but we don't have much of photosynthesis because plant is damaged. But in March, after we have a strong sunlight in the night, when we have a strong light, they have a good photosynthesis. So the plant did recover, have less of damage in later production period. So now we look at the yield. Basically, you see this is the Endeavor. You see the 12-hour one still have a slight high yield. Then the 16-hour we have a slight high yield or no reduction at all. So this one, the 20-hour red, we have some reduction. So these two, of course, we have a lot of reduction. So you see at the end, near the high later production period, for the 20-hour red, we have no yield reduction here. So the other one, we have the red blue together 16 hours during the daytime. So we are okay. So the same thing is for Trivanzo, the other Tematu cultivar. So basically from the thing you can see, we can reduce the light for the early period by 12%, cut down the energy and the electricity costs, all the light fixture by 12%. So this 75 we can do later. We can reduce by 25 in late production period. Also, we can use more than 50 micromole in late production period. So after that, then we move on, also did work on the cucumber, basically the 16-hour red blue, that's our control. Then we had the red blue together. That's only 2/3 of light intensity. Then we have the 16-hour by 8-hour blue. So we have no damage whatever after 3 months of lighting. Then we look at the photo accumulate, accumulate over the 24-hour period. All other one, of course, this one have a reduction during the night because of respiration. For the 24-hour, the red blue together, you have a continuous increase in the end. They basically no difference. So the yield, we have no difference. The large difference we get is less than 0.5%. So for cucumber, well, we achieved our goal. Mini cucumber, you can use 140 micromole, 2/3 light intensity, reduce light fixture by 1/3, electricity cost daytime by 1/3. So yeah, so we are now continue to work on tomato and pepper to achieve the same goal. In the end, I want to see thanks the AFC, the Foundational Science Program, OGVG, and the Canadian Greenhouse Conference, their research fund for support this project. Also, Living Group provide the light fixture, Roseland help with the transplant, University of Guelph also involved. So a lot of people, contribute the research. In here, I mentioned Jason, also Shannon, Long Chao, Creed, Celeste, Jingmin, and many other corporate students and greenhouse worker. I want to thank you for your attention. Thank you very much.
Thank you, Xiuming, for that presentation. I haven't seen any questions on there at the moment. And hopefully you've explained everything really well. A question I have, Xiuming, is in your 24-hour lighting versus the 12-hour lighting, the leaf structure is slightly different. In the 24-hour lighting, you got the very flat leaves, whereas there's the very curly leaves with the 12-hour lighting in the tomato crop. Do you think that's, what do you think causes that? Besides the entry component, do you think there's a restriction in movement of sugars or photosynthetics from the leaves into the fruit?
There are a couple of things. One thing is when you have a red light, the leaf stay relatively flat. So the second thing is when Jason measured the carbon, carbon, the starch, and the sugar in the leaf, he did not see any difference. Whether you have a 12-hour or 24-hour, basically the dynamic in the carbon, like in the leaf, is not affected. So that means there is no additional accumulation of the sugar in the leaf. If based on his photosynthesis, so they made more sugar, they did export out to the fruit. So they maybe export more. The other thing is like with normally with the lighting, you know, we have the leaf. That's always like it seems like there is a symptom we call the leaf, the light avoidance. It always kind of dripping down. So by doing like a red day and blue during the night, especially blue during the night, seem like we are able to overcome this light avoidance symptom and the light. Yeah.
So a question from Evan. If DLI is constant across treatments, do the day and night recipes really provide energy savings?
If we try to achieve the same DLR, so for the electricity part, the pure absolute amount you did not reduce. It is exactly the same for the electricity. Okay, so now we come to the part because you see it on the heating side, right? The heating, before you have 8-hour darkness, all your heat is coming from the boiler. Now you can see shown with that two figure, I don't know, we see that's a very important slide. You see the heat is met by the light, the boiler animal. So that's a big saving on the heating energy. So on the other aspect, before, even if we use the same amount of electricity, the one you use is in the daytime, is in the peak hour. We don't have enough power supply. If we go 1,000 acre, that's one thing. The second thing is during the peak hour, the electricity cost is higher. You know, electricity rate is high, while off peak hour during the night is lower. So although the absolute amount, the total amount is not reduced, but by evening them out, shift them into night, actually you reduce the cost, actually save the money on the electricity cost.
Thank you. Well, we're sort of running out of time. We have a few more questions. I'll ask another one here. On tomatoes, did you test the 16-hour R&B red and blue as standard, plus 8-hour blue, and compare chlorosis to just 16-hour regular red and blue?
We did not do like that direct comparison, but the way I see it, as you see in the figure with the 16-hour red, blue together, or 16-hour, we don't see much of a damage, very slightly. So both visually or use the chlorophyll fluorescent.
Okay.
We did do actually, sorry, I forget. The one in another trial that's 2 years ago, actually, in a 200 square meter greenhouse. Yeah, that one, we have a 16-hour red, a 16-hour red blue together. They base it at 16-hour, no difference. Yeah.
All right, one last question. It's a two questions, roughly the same thing. They're looking at fruit quality. One's looking at, is the fruit quality any different in terms of shape, size, shape, blossom rod, etc., short green shoulders, and also the sugar content or taste of the tomatoes. Can you just give that very short answer because it's the last question?
Okay. The short answer is no difference. We hardly see any BER, hardly no fruit odor. The plant is doing so well. In terms of antioxidant, the test, no difference. It's actually quite decent. And we also send the sample to Lone Charles lab to test the antioxidant. So once we get the result back, those one I can report later. Yeah.
All right, perfect. Well, thank you very much, Xiuming, for your presentation.